In this example, we're going to look at a hypothesis test for a mean using a z-test based on a standard normal distribution. So we've got a soft drink vending machine that is supposed to be dispensing 6 ounces per cup, but we have a suspicion that it is underfilling. So we take a sample of 50 cups. Out of those 50 cups, we got a mean of 5.9 ounces, so below the 6 ounces that it should be dispensing, and a sample standard deviation of 0.25 ounces. So we're going to test the claim that it is underfilling those cups. So what we need to do to begin with is formulate our hypotheses, and our null hypothesis is going to be that that there's no problem, that it's dispensing the correct amount. So H0, the null hypothesis, is going to be that the mean amount dispensed is 6.0 ounces as it is supposed to be. Our suspicion is that it is underfilling, and so our alternative is going to be that the mean is less than 6.0. So we're looking at a left-tailed test. Now we're going to compute a test statistic, and that's going to be x bar minus mu over sigma divided by the square root of the sample size. So x bar is our sample mean, 5.9. Mu is the value from the null hypothesis, the 6.0. Now, as would typically be the case in the real world, we don't know sigma, the population standard deviation, so we're going to estimate it using the sample standard deviation 0.25 divided by the square root of the sample size 50. Later we'll see that a t-test is a good alternative in this scenario where we don't actually know the value of sigma. Now, I could use any calculator to evaluate that test statistic and get that z-score, but I'm just going to go ahead and use Excel as my calculator to both do the computation for the test statistic and then also to generate the corresponding area under the curve. So I'm going to fill in the sample mean, which was 5.9, our population mean, which is assumed to be 6. That's the null hypothesis. We're assuming that the true mean amount dispensed is actually 6. Our standard deviation, 0.25. Our sample size, 50. And then I'm going to use a formula here to calculate that test statistic. And I'm really just using Excel as my calculator here. I'm going to put parentheses around the numerator. I'm going to do the x bar minus mu, sample mean, minus population mean. So I'm clicking on those values, and I get B1 minus B2, close those parentheses for the numerator, divide by a set of parentheses in the denominator, which is going to take then the standard deviation divided by the square root of the sample size. And here I'm just using Excel as my calculator. The advantage to doing it this way over typing it into a scientific calculator is now I could use this same worksheet on multiple problems by just changing the mean and the standard deviation and the sample size and so forth. But what I've got as a formula is equals B1 minus B2 divided by B3 over the square root of B4, and important to note that we've got a group of parentheses around the numerator and a group of parentheses around the whole denominator. And so we get that z-score of minus 2.83. we're going to calculate an area that corresponds to that z-score, that test statistic, and that requires the normal distribution function, or we could look in a table like Appendix A from the book. But it's easier to just use this function here in Excel, and it is equals norm.dist. I give it that test statistic as my input value, and then because we've standardized to z-scores, we're really working with a standard normal distribution, mean 0, standard deviation 1, and we always choose the option here true. So it's the norm.dist, and then the arguments are just the test statistic, comma 0, comma 1, comma true. And I can do that anytime I'm taking a z-score test statistic and trying to calculate that corresponding percentile. And I get 0.00234. Now, because this is a left-tailed test, that number right there, 0.00234, that really is my p-value. And so those calculations are going to give us everything we need to conclude the problem. So we came up with that test statistic of minus 2.83. So we're looking at a left-tailed area somewhere out here, almost 3 standard deviations below the mean for that test statistic. So our test statistic is a z-score. It's a position in our normal distribution there. And we were just looking for the area of that tail. That's our p-value. And it was 0.00234. And what that p-value tells us is the probability that we would get a sample mean as extreme or more extreme than this value of 5.9 if the true mean was really 6. There's only a 0.00234 probability that we would get a sample mean of 5.9 from a sample of 50 cups if the true mean was actually 6. Because we're testing at the 0.05 significance level, that's our alpha equals 0.05, we conclude the test by comparing the p-value to alpha. Our p-value is less than alpha, 0.002 is less than 0.05, and based on that, our conclusion is that we reject the null hypothesis. So we always conclude a test by deciding whether we reject or do not reject. Okay, so because we reject the null hypothesis, we could say that we do have evidence to substantiate the claim that the mean is in fact less than 6 ounces.